I'm going to talk about folds. Folds are planar layers of rock that have been deformed into the folded shape. This image that you're looking at shows a fold, something called an aniform, and there's an oil well sitting right at the top of it, which is caused by the fact that the hydrocarbons migrate up and they get trapped in the top of these folds. So folds have economic significance, and what we're going to be talking about today mainly is the different ways of describing and categorizing folds. So like when we encounter a fold in the field, like how do we record, what do we measure, how do we describe it, how do we mark it on our maps, that kind of thing. Folds. Okay, a fold is a curviplanar arrangement of initially more or less planar geologic feature. I suppose it could be another kind of feature as well. You can fold paper. Okay, so something that used to be a plane and then it's been bent. So we'll start by talking about two folds that are related to faults because we've been talking about faults lately. So fault-related folds. So the first of these is a fault bend fold. So this is a fold that happens because there's a fault at a deeper level. So if we have a fault here, and it's carried up some stuff. Okay, so here's this fault, and because it's gone up this ramp and then flattened out, the layers above it are folded. So we call that a fault bend fold because the fault's taken a bend. We also have a fault propagation fold, which is another propagation fold. Fault propagation fold's another type of fold that happens because there's a fault at depth. So in this case, we have a fault coming along and it's starting, but it hasn't really gone too far. So what happens is the layer above it is pushed up, but there's no actual fault at the surface. These tend to happen, the fault bend and the fault propagation folds tend to happen in sedimentary layers at fairly low temperatures. All right, let's try another one here. So the third type of fold that's related to faults is a drag fold. So here we have a fault. Let's say this could be a strike slip fault, or it could be any kind of fault, and there's often an area near the fault where a layer, if it's fairly planar, when the faulting happens, so this side of the fault is moving that way. So sometimes it'll get actually kind of like dragged. That layer will get dragged into the fault. So maybe this, based on the way this fault is going, probably this layer would originally have connected down here. Okay. So there's a fold, this planar material, maybe it's a layer of limestone or sandstone or something, is curved and folded because of the fault. Okay. So next we'll talk about there's a kind of exhausting literature on fault, sort of characterizing folds. We're not going to get too far into it, but we'll introduce some terminology, descriptive terminology. Okay, so most terminology assumes that folds are cylindrical. So what does that mean? Cylindrical means they can be described, by moving a line parallel to itself through space. So think about like a long exposure in a camera. Like if you leave the lens open on a camera at night, and someone has like a light stick, you could wave it around. So you can move the light stick around without changing its orientation, without changing its plunge and trend. It's just moving in space, but it's still pointing in the same direction and tilted the same way. So we can sort of illustrate that. So here's we're going to do a little 3D drawing here. Okay, so that's the bottom side. It's the bottom side again. Okay, so we've moved this, like you could think of this as this plane that's curved, or it's a curved feature that's made out of a bunch of lines that are all, if I drew it right, all exactly parallel to each other. Okay, so that's what we mean by cylindrical. Clearly, not all folds are going to be cylindrical. But we often, just to try to keep things as simple as possible, we assume that they're more or less cylindrical. Okay, and so there's our cylindrical fold. And the orientation, in other words, the trend and plunge, of the line has a name. It's called the fold axis. Okay. The fold axis is something that we can often determine when we encounter a fold. Okay. So let's draw a typical, like a simple fold. Okay, so this is a fold that's made out of a few different layers. Okay, and then underneath that layer, just dash it. Same with this one. Okay, so typically a fold is a point where the curvature is the greatest. It's often like, I've done it better here, this little one. It's like a kind of a sharp corner. So often a fold will kind of come up and there's sort of a peak to the fold. If we connect a variety of, in our imaginations, we connect those points to the maximum curvature for different layers of a fold, we can identify a plane. So this plane that's formed by connecting all these points in 3 dimensions of sort of the peak of the fold, this is called an axial surface. So these points where the curvature is the greatest let's label these. Okay. These are lines, maximum curvature. So this would be a line of maximum curvature for this top layer. And most folds have one of these. This is called a hinge line. So we can also call the center near the hinge of a fold the core, and we call the sides limbs. So there's a limb over there, and there's a limb over here. So many folds are what we call axial planar. So let's write that down. Many folds axial surface are planes, but this isn't necessarily the case. So the one I've drawn, this axial surface where we've connected all the hinge lines, that surface is a plane. So we call this axioplanar. So an axioplanar fold. But doesn't have to be like this. Even for a cylindrical fold. So you can imagine a fold like where the layers, here's the axial plane for one layer, but then the next layer kind of, the axial surface would bend, okay? So this would not be an axial planar fold. Classifications of folds. So if a fold here's the axial surface of the fold. This is what we call an upright fold. So the axial surface in this case is vertical. Okay, if we have a fold where the axial surface is tilted, we call that inclined. In an inclined fold, all the strata are upright. Okay, so none of these layers have been like flipped over. So if they have, if you've got a fold that has, so over here, this is overturned, upside down. We call this an overturned fold. So the original sedimentary way up here is upside down. If the fold, if the axial surface is subhorizontal, subhorizontal axial surface. We call this a recumbent fold. And if both sides of the fold both limbs of the fold have been overturned so that the original way up is now down, we call this inverted. So here, both limbs face down. Okay, so more or less complete description of a fold in the field includes the following. So we would need to know the trend and plunge of the fold axis, and also the strike and dip of the axial surface. So see if you can take a moment and imagine how you could have a fold that has an axial surface that has a certain strike and dip, but the trend and plunge could vary, or vice versa. Where you could have the trend and plunge of an axis and the axial surface could be different. We're going to demonstrate how a fold could have the same fold axis, but different axial plane. Okay, so here's an upright fold. So the lines here, we could make this. We could take a line, is indicated by the pen here, and without changing its trend and plunge, we could describe this surface. Okay, so that's what we mean by the fold axis. And the blue lines on this paper are the fold axis. Okay, and if we had imagined like a bunch of layers on top of this, also, curved in the same way, the axial plane of this fold would be vertical. So it would connect the hinge, this point. The hinges, this point where the curvature is the greatest, of all these different layers would connect into a vertical plane. Okay, without changing we can change that plane without changing the hinge, the fold axis. So we haven't changed the orientation of the blue lines at all. So they're the same. They haven't changed. They have the same trend and plunge. But now the axial plane is horizontal. So this is an example, and we could do all manner of changing. Axial plane is now getting steeper, and our blue lines, our fold axis is not changed. So that's an example of how we can have the same fold axis but very different axial planes. And so let's do the other case now. Okay, so here we have that horizontal axial plane. Fold axes are coming in and out towards you. But now if we just rotate this, so the axial plane isn't changing, it's still horizontal. But the fold axis, which is that blue line, its trend is changing. So we need both to know the trend and plunge of the fold axis and the strike and dip of the axial surface. Okay. So we can also talk about interlimb angle descriptions. Okay, so as we're describing folds, some folds are going to be sort of not that folded. And if we take the limbs and just kind of fit a plane to them, if this angle here is sort of between 120 and 180, we call that a gentle fold. And sort of more, we call it an open fold if that angle is between 70 and 120. So here, so we just take the lems and extrapolate. We call it closed if it's 30 to 70, and tight if it's 1 to 30. And if the limbs are actually parallel to each other, so the limbs have the same dip, we call that isoclinal. And we'll see examples of isoclinal folds in the Manhattan schist. Okay. All right, so and notice that all those folds have the same axial surface and the same could potentially have the same trend and plunge of their axis. So there's it's kind of amazing how many different numbers are needed to really characterize a three-dimensional shape. Okay, so the most famous or most important terms to know for folds are antiform and synform. So an antiform is a concave down fold. So a fold that has a shape like that relative to Earth's surface. So this would, this would be surface of the Earth. The synform is a concave up fold. So it's a fold that is that shape. And when folds affect sedimentary rocks or stratified rocks, with sort of with knowledge of or we know the ages, we know which way is which layers are younger than the others. Then we can talk about an anticline, which is a fold in which older rocks occur towards the core. And the syncline the fold in which younger rocks occur towards the core. Okay, so for an upright fold, where the rocks aren't like flipped over or anything, it'll be younger. This fold would be younger in the middle. This would be a syncline. So typical syncline has a synform shape. And same with anticline would be, if you took even these same layers and folded them into a shape like this. So the youngest layers on top. This would be older in the core. So this would be an anticline. So sometimes you could actually have, if you took this and flipped it over, you could have a fold that was an antiform. So let's just point out that older is still in the middle. So we just took this, we rotated 180 degrees, flipped it upside down. So the oldest rocks are in the core, So it's still a syncline. It's this is still an anticline, but it has a syn form. So we call that a synformal anticline. So we're not going to actually see those, but this is part of why we have this distinction between the forms, antiform and synform. So if we don't really know anything else, we look at the shape. We say, oh, that's an antiform. It kind of has an A shape. That's how you can remember, maybe. Looks like an A, antiform, and a synform. But if we happen to know, oh yeah, actually the rocks at the base of this, lower down, are older, it hasn't been flipped over, then we would call it an anticline because we have more information. And we'll move on to map symbols now for folds. And with these, the arrows point in the dip direction. Okay, so these are map symbols. So we could imagine like north is this way. Okay, so we could draw down the middle of the fold a line, and then imagine the limbs dipping off the way that the arrows are pointing. So this is a symbol for an anticline. It's an anticline that's striking northeast. So the hinge line that we've drawn here is pointed towards the northeast. So it might be actually better to say trending northeast for that if you're thinking of the line, but the axial surface would be, the axial plane would also be striking northeast. So a syncline has the limbs tilted in towards the center. And these can curve if the trace of the fold bends, we can curve that line. So that's a syncline. We talked about overturned folds, so that's where there's like one of the limbs, the rocks have been flipped over from the original orientation. This is a symbol for an overturned anticline. And here's a symbol for an overturned syncline. So if you're looking at these from the side view, so just underground. So an anticline, just to remind you, would look like that. A syncline, like that. Overturned anticline is where one of the limbs, like that. Overturned syncline. All right. So some other particular folds that have very particular shapes of folds. So if the rocks are folded really with like very tight hinges and have pretty planar limbs, we call this a kink. A kink or chevron fold. So here we have tight hinges, and planar limbs. If you just have a bunch of rock layers that are dipping all the same way, we call that a homocline. This is a uniformly dipping set of strata. I've actually never encountered one of those. At some point, those are going to have to like go back to, reveal that there's a fold at a larger scale. These are fairly common though, a monocline. So monocline is a fold with only one dipping limb. Often monoclines are, the scale of, this could be a kilometer. These can be very large. Sometimes you have folds that have different wavelengths of folding associated with them. This is called disharmonic. And this occurs in beds that have different viscosities. So some are stronger than others. So let's just look at some slides of some folds. So this is illustrating that idea of the cylindrical fold, and its opposite, which would be a non-cylindrical fold. So here this material has clearly been folded, but the hinge line is curved. Examples of a monocline, a synform and antiform, where we don't know the relative ages of the two layers that are shown. And here we're showing the Younging direction. So these little sort of Y-shaped things are pointing in the Younging direction. So these rocks are not upside down. So this would be like the surface of the earth up here. So this is a normal syncline, a normal anticline. And then if we were to flip these over, we get our aniformal syncline, synformal anticline. Don't worry too much about those. Point of a syncline, though, is like the syncline isn't necessarily the shape. It's the fact that it has the youngest rocks in the middle. That's the definition. So here we have a fold that has sort of two aspects. There's a giant fold. This kind of thing tends to happen in really high-grade rocks that deform when they're very hot. And then that whole fold has been folded again. So there's an axial surface that kind of comes along relatively horizontally, like I'm tracing out, and then there's another axial surface for the second generation of folds that's pretty much vertical. Here's another one, and another one. And you can see they've named the anticline, syncline, at different parts of that, depending on whether the layers have been flipped over like they have down here, or if they're right side up. Here's an example of some disharmonic folds. So there's folding of this layer as a different wavelength than that little layer in there. So this layer is probably, it's thinner, so it's a little bit weaker. Here's an isoclinal fold. So isoclinal folds, remember, means that the two limbs on either side are parallel to one another. These are really important because sometimes you find a bunch of layered rocks. Like if you didn't see that fold there, you just saw this layering, you wouldn't know that this stuff had experienced like an extreme deformation, that had been like completely like flipped around. Here's some more isocline of folds. So the limbs parallel to each other, back and forth. So this would have been originally this white stuff would have been like a quartz vein, and then this rock was deformed so severely that it's just been kind of mushed up. Here's an example of a large chevron fold. So it's got these planar limbs. Chevron folds tend to happen in pretty relatively cold rocks. So the deformation all is happening really in one plane there. Here's an example another example of two generations of fold. The camera lens for scale. So we have our first fold, which is layers kind of just coming around like this. So the axial surface of that is pretty much, looks like it's pretty horizontal here, and then it kind of bends down, it looks like. And then there's another axial surface that's vertical. If you just zoomed in on one of these little folds here, you would draw the axial surface through those. So this would have, axial surface 1, which is a little bit wobbly, and then axial surface 2, which is pretty much vertical. And here's another example of two generations of folds. So we have an isoclinal fold here. The limb on this side and this side are the same. It comes up and then back down. And then that surface that fold has been folded again.